All right, let's continue on with Chapter 8 here. You've already noticed on D2L that we are going to pretty much eliminate 8.2. Most of the stuff that we do here is either dead end or retaught in Chem 30, so don't worry about graphical analysis. We won't worry about that one this time around. So you can take that out of there. Don't worry about precipitation completeness. Okay, that's one that comes up in one of our labs only. So I wouldn't worry about it there. And then, of course, selective precipitation can also go, since that is also one of our lab-only investigations. So 8.2 is going to be removed to make this last chapter a little bit more simplified for you. Next is just kind of reviewing limiting and excess reagents. Now, I did introduce these with some example questions in Chapter 7. All right, it is an important idea. It comes up much more for us here as we start doing some of our experimental stoichiometry and some of our other chemical analyses. So let's just review a couple of things. These are all question styles that you have seen before. I'm just kind of reteaching the topic here. So we'll go through it fairly quickly. In this one, we're being asked, what chemical amount in moles of lead nitrate must be added to precipitate all of the chloride from your sodium chloride solution? So in other words, this one is your limiting reagent. We're trying to make sure that it is completely consumed. In order to be able to do this one then, we're going to use the knowledge about our limiting reagent to try and figure out what quantity of the other reagent we need. For this, remember, stoichiometry always predicts a minimum amount. I'm going to start with my concentration of 0.143 moles per liter, since that does put moles in the correct spot. This is also for NaCl. I like to put the species in there. And now it's just going through the factor label method until I get down to just moles. So I'm going to multiply by my volume that I've converted to liters. And now I have moles of NaCl. So now I can use my mole ratio between what I was given and what I want. And so I do have 1 part lead nitrate, and I do have 2 parts NaCl. So you can see that NaCl as a species now disappears from the problem, and the remaining units are moles, but they're now applied to lead 2 nitrate. So I have the correct units that I'm looking for. I have the correct species. I just have to run this through my calculator, and what we end up with is 0.00715 moles. And so I'll probably put this into scientific notation just to make it read a little bit easier. 7.15 times 10 to the negative 3 moles of lead 2 nitrate are required. Okay, so it's very simple when we do have the limiting reagent identified. It's your starting point. It is the limiting quantity that makes the whole reaction quantitative, as they say. All right, so with respect to that, that is the amount that is required to precipitate all the sodium chloride. But remember, that would take forever and a day to finish because you're waiting for the last few atoms of each to bump into each other. So we're looking for an appropriate chemical amount. Remember, we don't want to be wasteful. We want to make sure that there is enough of this to quickly react all of the NaCl. And so we use that 10% rule. So I multiply this by 1.10. And when I do that, we end up with a new value of 7.865 or 7.87 times 10 to the negative 3 moles required as an appropriate chemical amount. So remember, there's that 10% excess idea. Okay, now that's a little bit unrealistic or a little bit simplified for us because not all the time is the limiting reagent given. And so again, remember how to identify a limiting reagent is that we do have to run stoichiometry twice, and we have to test each starting quantity to see which one produces the least amount of product. That's the most simplified way of doing the limiting reagent part. Once you've identified which one runs out first, that is your limiting reagent. The other one is by definition your excess. And remember, all of your stoichiometry is based upon limiting reagent amounts. So, when we're going through this, remember to find the limiting reagent, you must do this stoichiometric prediction twice. Please do it for just one product. Pick one. It doesn't matter which one you use. Pick the most simplified one if there are two. And remember that you could just find out the amount of moles and then do any necessary calculations after that. So we'll get into another example here. We're taking a look at the Haber process, and it produces ammonia gas by combining the elements. In this case, you can see that we have two starting quantities and no indication with the wording to know which one runs out first. So we have no choice here but to go through and test to see how much ammonia is made from nitrogen and how much is made from hydrogen. Whichever one produces the least, I have as my limiting reagent, and I can go and then answer the questions that are being asked. So for this one then, I will run through my 100 grams of hydrogen. I will convert that to moles with molar mass. Okay, it is 2.02 grams for every 1 mole of H2. Grams are now gone, so I have moles. I can now do my stoic ratio, and you can see it's 2 parts ammonia for every, 3 parts hydrogen. Hydrogen now goes, and this is an appropriate place to stop. Okay, it saves me a couple of steps down the road. So when I do this, I find out that I get 33.003 moles of ammonia. I need to check now to see what 200 grams of nitrogen is going to get me. So for this one, run through my molar mass, and it is 28.02 grams for every 1 mole. I now have moles of nitrogen, so I can now do its stoic ratio, and you can see it's still 2 parts ammonia, but now only 1 part nitrogen. Nitrogen now leaves the equation, and I can get my answer. Do that, and you find out that you get 14.275 moles. So this means nitrogen produces less ammonia than hydrogen, so nitrogen is now my limiting reagent. I can now answer the question and figure out how much mass of ammonia I have. I just have to finish off this one calculation right here. And I will use the molar mass of ammonia, canceling out the moles, and it is 17.04 grams per mole. I now have grams of ammonia. That's the answer I was looking for, and it works out to, in our rounded answer here, 243 grams produced. We had one more question to answer here. It was asking how much of the excess reagent is going to be left over. So if you're not limiting, you are the excess reagent, and so I must figure out how much hydrogen is actually used when all 200 grams of my nitrogen is used. So I'll just start over one more time. 200 grams nitrogen. Turn that into moles by using its 28.02 gram per mole molar mass. Grams are gone. I can now use my mole ratio because I am in moles, and you can see that it is 3 parts hydrogen for every 1 part nitrogen. Different mole ratio than what we've used before. Nitrogen now leaves the equation, and I have moles of hydrogen, but I can't really compare moles to grams very easily, so I should turn this into a gram quantity. And hydrogen is 2.02 grams per mole. Moles now cancel out, and you have grams of hydrogen. Figure that one out in your calculator, and you get 43.254 grams used. The question was asking how much is going to be left over. So if I had 100 grams and I used 43.254 grams, then the leftover amount, when I round this appropriately, is going to be 56.7 grams. Okay, so there's an example of a limiting reagent excess reagent problem that was completely open-ended. We only really saw one of those, a couple of those in Chapter 7. We see them here again, as we get into chapter 8.3. All right, 2 more examples to go, and then a homework assignment. You'll find that in the next video.